In question 1, we are asked to find a three-dimensional relative velocity of a beacon as viewed from our Millennium Falcon. So using our S and S' reference frame terminology, we have the Millennium Falcon as the reference frame S' because it's moving with a velocity relative to our mechanic in the reference frame S. We've been given the three-dimensional relative velocity of the beacon from the reference frame of our mechanic, so from our reference frame S, as Vx is equal to 0.1 c, Vy is equal to 0.6 c, and Vz is equal to 0.4 c. So we are looking for the components of that velocity, which are Vx dash, Vy dash, and Vz dash. We also know that compared to our mechanic, or relative to our mechanic, our reference frame S dash is moving with a velocity of 0.65 c in the y direction. So this is slightly different to the derivation we had in the video, because in this case the relative velocity of our reference frames S and S dash is in the y direction. So what that means is we have to adjust our Lorentz transform slightly, and so that gives us our three formulas for our relative velocities, Vx dash, Vy dash, and Vz dash. And you'll see because the relative velocity of the reference frames is in the y direction, it's our formula for Vy dash relating to Vy that has that extra component on the top and is missing the gamma on the bottom. So each of these three formulas have the same component in the denominator, which is 1 minus uy Vy on c squared. So we'll solve that first, and by substituting in our values of uy equal to 0.65 c and Vy equal to 0.6 c, we get that that component is equal to 0.61. And we also need to find our component, our gamma. So we know gamma is equal to 1 divided by the square root of 1 minus u squared on c squared, where u is the relative velocity of the reference frames, in this case equal to 0.65 c. So substituting that in, simplifying and solving, we find that our gamma is equal to 1.32. So now we can just substitute in all of our values into our Lorentz transform equations, and we find that Vx dash is equal to 0.12 c, Vy dash is equal to negative 0.08 c, and Vz dash is equal to 0.5 c. In question 2, we have what looks like an awfully complicated question, but once again, solving this question is actually somewhat simple and is down to the setup, so the translation of the problem, and keeping it neat. So before I figure out what it is that I want to find, I will set up my question so that I can understand what's going on. We want a few things from the reference frame of the mechanic. So I'm going to call that reference frame S, and we're told that from that reference frame, from the point of view of the mechanic, the speed of the Death Star is equal to Vx. So we know that the Death Star is moving relative to the mechanic, so I will call the reference frame of the Death Star S dash, and from the point of view of S dash from the Death Star, we know that the TIE fighter is also moving with a speed of Vx. So Vt dash, the speed of the TIE fighter in the reference frame S dash, is equal to Vx. And finally we have the TIE fighter. So the TIE fighter is also moving relative to both the Death Star and the mechanic. And so as not to confuse myself or to confuse the reference frames, I will call the reference frame of the TIE fighter S double dash. And we know that as seen by the TIE fighter, the missile is moving with the speed of Vx. So Vm double dash, the velocity of the missile in the S double dash frame, is equal to Vx. So with this setup and with my terminology as I've defined it, we're looking for the speeds of the TIE fighter and the missile as seen by the mechanic. So we want Vt and Vm. So now we can start to solve. In part A, we're looking for Vt, and we have a value for Vt dash. So we can use our Lorentz transform between frames S and S dash, and so then we get that Vt is equal to Vt dash plus u divided by 1 plus Vt dash u on c squared. Where in this case, because we're transforming between the velocities S and S dash, u is the relative velocity of S dash relative to S. So that is, it's the velocity of the Death Star as seen by the mechanic. So that's equal to Vds, which we know is equal to Vx. And we also know that the velocity Vt dash is equal to Vx from our initial setup. So substituting those values into our Lorentz transform for Vt, we find that Vt is equal to 2Vx divided by 1 plus Vx squared on c squared. In part B, we will follow exactly the same procedure as we just did for part A, except that the maths is going to be slightly longer. So the maths part will be slightly more complicated, but the translation of the problem will be the same. So we're looking for the speed of the missile relative to the mechanic. We only have the speed of the missile relative to the TIE fighter, so we are going to be looking to convert between our reference frames S and S double dash. So that is, we will be using the Lorentz transform between those two reference frames. So we have Vm is equal to Vm double dash plus u divided by 1 plus Vm double dash u on c squared. And in this case, since we're looking between S double dash and S, u is the velocity of the reference frame S double dash relative to S. So that is, it's the velocity of the TIE fighter relative to the mechanic. So that we would write as the velocity Vt, or as the speed Vt. And we found that in part A to be 2Vx divided by 1 plus Vx squared on c squared. So that's our setup. And now we just need to substitute in those values and solve. So we know that Vm double dash is equal to Vx, and we have our equation for Vt. So I'll split that up into the numerator and denominator, and I'll find a simplified expression for each, and then I'll recombine those expressions back into a formula for Vm. So our numerator is equal to Vx plus 2Vx divided by 1 plus Vx squared on c squared. When I expand that out, both the numerator and denominator of this equation have a fraction on c squared. So I will multiply top and bottom. So I'll multiply that fraction by 1 by multiplying top and bottom by c squared, and that gives me a formula. 3Vx c squared plus Vx squared divided by c squared plus Vx squared is equal to the numerator of our equation for Vm. Looking at the denominator, I'll do the same thing. So our denominator for Vm is equal to 1 plus Vx on c squared times 2Vx divided by 1 plus Vx squared on c squared. And expanding that out and simplifying it, once again we get that that's equal to c squared plus 3Vx squared divided by c squared plus Vx squared. So that's quite nice, because now both our numerator and our denominator are fractions with each with the same denominator of c squared plus Vx squared. So putting those two equations back together to get our expression for Vm, which is what we started out trying to find, we simplify and we get the equation 3Vx c squared plus Vx cubed divided by c squared plus 3Vx squared is equal to Vm. Now what I want to do is, I'm going to multiply through again by 1, but this time my 1 will be the fraction 1 on c squared divided by 1 on c squared. And the reason that I'd like to do that is because that quantity, v squared, or v on c, or v squared on c squared as we often see it, is a common quantity when dealing with relativistic equations, and I just like my equation in terms of that. And so when I do that, I find that Vm is equal to Vx times 3 plus Vx on c all squared divided by 1 plus 3 times v on c all squared.